Alright, for the first question in tutorial 2, we get a scenario and we're asked to just think about what a specialist decided. There's a company that makes some cellular phones. They don't want to put some GPS mapping feature on the phones. There are two products that they're considering. I don't know if you guys are watching Smile Jamaica this morning, where they talked about the Garmin system that they put on the navigation system they put in the vehicles that Mona Jais is selling. Yeah, well, that's where one of the people that have to configure the system. Well, the Garmin is actually something that's available, but to get a country's information into it, then somebody's going to have to take the task of configuring that and then loading it onto the system. So Mona.js did it with Dr. help. So right now they're on the market. Now, of course, since it's a very small device, then certain things become very important. These big devices we have in front of us normally have a whole heap of storage, normally have a whole heap of processing power. So we do normally, and most of us, most of us have been using computers for things like word processing and presentations. So if we sit down and wait a couple of minutes, big deal. However, there are certain applications that need to happen in close to real time, if not real time. So with those applications, you have to start thinking about the time complexity, how much things need to be considered, and once we look at those variables, how fast can we come up with a decision? And knowing the worst case of time that a decision needs to be made in will determine whether or not the system will be able to do the job. For example, you could have automated landing systems, but maybe we don't trust these computers and we maybe don't have powerful enough computers to actually do that we all trust. So that's why we still need a human being there, because the time complexity of the programs that need to be run on most systems is too large. And if something happens at the last minute, you don't want to have the program waiting. An hourglass won't help. No way. Alright, so we're told that one algorithm will take about 6 calculations per landmark. And they use 1 integer to store each landmark. So that's 6 calculations second per landmark. That tells you the time complexity. 1 integer per landmark, that tells the space complexity. And that produces maps with a margin error of up to 26 meters. That tells you how precise it is. It doesn't say it's inaccurate. It tells you that it introduces that level of imprecision. On target requires a mixture of 6 integers per landmark for storage, use up much more space, and 16 calculations on every other landmark per landmark. So that's a whole heap more calculation, so it will take more time. But it gives a half margin of error, so it's very precise. So the company recommended the less precise one. Question is, what do you think of their choice?
The less precise. Probably a little bit faster. And at least it'll be more real time.
So do you think it's a good choice or a bad choice? It really is. It's not a right. There won't be a right or wrong answer.
It's going to be off because if it's off by 26, the error margin of error is 26, and the other one is half. That's a
Okay, for cell phones, who really cares if you're 26 meters off? You walk around something 26 meters away, you can see it and then correct yourself. Now, would you make the same recommendation for an aircraft navigation system?
No.
There you go. And you'd assume that they would have maybe even custom built hardware that can actually execute these computations pretty quickly. And that's what cars for the algorithms you compared, where there was the time complexity and the space complexity, and the precision that you got from it. Alright, so in the next section, we'll look at the same B to the N algorithm, where we have pretty much the same function here. So we're asked to, instead of powder, use XPT1. We can, let me just put in that function name. And now we're asked to analyze that algorithm. Now first, in analysis, there are several steps. Remember what steps are, please. Well, it's actually written out over leaf. Where are you? You're looking at page 2? Good. Well, each question there actually corresponds to each step.
Okay.
So the first step, so that's, yeah, it's a trick question. So to analyze an algorithm, first we're going to identify the basic operations. Then we need to figure out something that tells us what the size of input will be. Then we're going to write down the some recurrence relation, and then we're going to solve the recurrence relation. So basic ops in this case would be remember, basic operation is some constant time operation that you're going to identify different things that need to be done. Now you want to choose constant time operations as the basic ops. Granted, sometimes you may come up with an operation that you may not be able to see inside, or you may have analyzed it before, and you are able to assign a time complexity to it. So that's an operation that you can take into account. But right now, we don't have any of those in this simple case. So we look at different things that need to be done, the things that are done, and count them as operations. So this is one operation. Should equal the multiplication and subtraction. So basic operations are equal, and what would be a suitable definition for the size of input? Hold on. Alright, there will be one or more of the arguments that come to the function. That will tell how big the input, how much data the program is working on. That's all. Now, in industry, it's become a standard or a common practice for the size of input to be called n. So, granted, in the course, most times you're going to have a variable named n, and most times that variable named n will correspond to the size of the input. But other times you may have to give a description based on the function of what the size of the input is. So, in this case, the size of the input is the variable n. Alright? Now, we now need to count the instructions and then come up with an expression to say how much work is done given that certain things happen. Alright, now when you're counting instructions, you're going to take into account that several options are available. this could happen or that could happen. So when you're counting instructions, I will just say step one, step two, size of n, size of input is n. Now if n equals 0, only one thing happens. Just the equal sign.
Right.
So the time that will take to execute the function will be equal to 1. If n is greater than 0, then how much things happen? This is going to happen first, but you still need to check. So that's 1, that's 2, that's 3. And then does anything else happen?
Checks again.
Checks what? We're here. Let's just look at this, and the answer is right here. So it does these three things, and then it calls us again. The function expt. But this time, what's the size of the input? Exactly. 3 plus the time to execute the function working on n minus 1 things. That's what that means.
So 3 plus t bracket n minus 1.
T of n minus 1. Now the way it's written out, I'm going to take this off. One if n equals 0, n minus 1 equals 3 if n greater than 0. So that's the standard way of writing a reconstruction.